Okay, this is a lesson on zero and negative integer exponents. Start with the zero exponents property, which says that if I have any base to the zero power, that equals 1. And that might seem kind of random, but not really when you look at the evidence. Let's consider 2 to the 4th divided by 2 to the 4th. If we use the quotient of powers with equal bases property, that would have to be 2 to the 4 minus 4, which equals 2 to the 0. But if you think about what that has to be, you think that 2 to the 4th would equal 16, and divided by 2 to the 4th, which also equals 16, that equals 1. So you can conclude that 2 to the 0 has to equal 1. You can also think about powers with the same base, and if you look at them in descending order, like 2 to the 5th would equal 32. 2 to the 4th is going to be half of 32, which is 16. 2 to the 8th is half of 16, which is 8. 2 squared is half of 8, which is 4. 2 to the 1st is half of 4, which is 2. So therefore 2 to the 0 has to be half of 2, which is 1. If you think about powers of 3, 3 to the 4th is 81. 3 to the 3rd is 27, which is 1/3 of 81. 3 squared is 9, which is 1/3 of 27. 3 to the 1st is 3, which is 1/3 of 9. So 3 to the 0 has to be 1/3 of 3, which is 1. So let's look at some examples here. So if I have 9 to the 0 power, just following the property, we now know that that has to equal 1. Now when you have 5 x to the 0 power, that really actually means 5 times x to the 0 power. So it's only x that's taken to the 0 power, so that means 5 times 1, or 5. But when you have 5x to the 0 power and both the 5 and the x are in parentheses, you can just think of all of that taken to the 0 power, so that just has to equal 1. Same thing in this next example. Even though I have all of this going on inside of the parentheses, since all of it is taken to the 0 power, that means that this expression taken to the 0 power has to equal 1. Now let's look at the negative exponents property. That says that if I have a base taken to a negative exponent, that just means 1 over that same base taken to the positive power. This is also not random. Let's talk about what we know. If I have x cubed divided by x squared, that means x to the 3 minus 2. You subtract the exponents when the bases are the same. So that equals x to the first. Well, the same rule would have to be followed when the exponent in the numerator is less than the exponent in the denominator, and you would end up with a negative exponent. So what does that mean? Well, we can kind of easily see what that means if we thought about what we knew before we knew about negative exponents. That would mean that you have x times x in the numerator over x times x times x. So when you cancel, that x and that x cancel, and that x and that x cancel, so this equals 1 over x. So if you look what you had above, and that means 1 over x to the first power, so x to the negative first power equals 1 over x to the first power, which is just 1 over x. If you then made the problem x squared over x to the 4th, the subtraction rule for quotient of powers of equal bases would tell you to subtract the exponents. So this would be x to the 2 minus 4, or x to the negative second. But if I looked at this in terms of canceling, I realize what the meaning of x to the negative second is. That just means I have more x's left over in the denominator. So now I have 2 x's left over in the denominator, so this all equals 1 over So this all equals 1 over x squared, so that's what all this has to equal. So that means that x to the negative second has to equal 1 over x squared. Alright, so also embedded in this unit is, or this section is, how we handle variable exponents. And so we just want to follow the same rules. So if I'm looking at y to the 3m plus 2 times y to the negative m, this would be multiplying powers with equal bases, so we would want to add the exponents here. So this would be y to the 3m plus 2 plus negative m. I'm adding the exponents for bases that are the same. And so here I'd want to combine my like terms. 3m plus negative m is 2m. So this would be 2m plus 2. Here I have, now that in this example I'm going to have a power taken to a power, so I'm going to want to multiply here, and I'll actually use the distributive property. So I'll have y equals m minus 3 times 4, so that would be y to the 4m minus 12. Same thing this next example, although one thing I can do here is I can take this, I can use the negative exponents property, and before I do distribution I'm going to I'm not going to change the signs of things in the denominator, in the parentheses, the exponent for the power in the inside the parentheses, but I am going to change the sign of the exponent outside the parentheses, since I went 1 over that amount. So now I can multiply 1 over y to the 2 minus n times 4, and that would be 1 over y to the 8 minus 4n. And then if I have x to the 3n over x to the 6n, I'm going to subtract the exponents. So that would be x to the 3n minus 6n, or x to the negative 3n. And I guess we could leave it like that, but probably best to leave it like 1 over x to the 3n. Alright, now let's some examples where we're using all the properties we've learned so far in chapter 4. So if I have 5 to the negative second times 5 to the negative fourth, all that divided by 5 to the negative sixth, let's put together the two powers in the numerator by the product of powers with equal bases property. So that's going to add the exponents. That's going to be 5 to the negative 6 over 5 to the negative 6. Since the numerator and denominator of this fraction are the same, we're going to conclude that equals 1. Alright, in this next example, I've got negative 6r to the negative second. The first thing I'd like to do here is to make that 1 over, I'll leave the parentheses for now. I want you to keep working, and that needs to be a positive exponent. I want you to keep working down the page in these. I'm running out of room here in my I'm running out of room here, but so let's go up here. So that means I'm going to distribute the 2 because I have a power of a product in the denominator, so that's going to be negative 6 squared times r squared. That's 1 over 36r squared. And for the next example, I have x to the second times y, all that to the negative second power. Once again, I'm going to make that 1 over, leave the parentheses for now, to the positive exponent. Then I'll distribute that using the power of a product rule, and so that's going to be x to the 2 times 2 or 4, and y squared. Alright. Alright, so next I'm going to look at this example over here. We have x to the 12th times x to the negative 7th and divided by x cubed times x to the 4th power. And I'm just going to combine the powers in the numerator and denominator first. So I'm going to add the exponents for x to the 12th times x to the negative 7th and get x to the 5th. Then I'll have x to the 7th in the denominator. I know that I have 2 extra x's in the denominator here. The rest will cancel, so that's just going to be 1 over x squared. In this example right here, I have a to the negative 2nd times b to the negative 3rd to the negative 4th. I think what I'm going to do first is change this to 1 over. I'll leave everything alone in the inside the parentheses, but I'm going to change the exponent for the power there outside the parentheses to a positive 4 since we moved everything to the denominator, and then I'm going to use my power of a power property, so I'll have one over a to the negative 8th, I multiply there, times b to the negative 12th, and I can move both of those powers up to the numerator as a positive power. So that's going to be 1 over, it's going to be a to the 8th power, b to the 12th power, so that I can, just as I can change the sign going to the numerator denominator of the power of the variables, I can go the other direction as well and move negative powers in the denominator to positive powers in the numerator. So next example, I have b to the 5th divided by b to the negative 2nd, all that taken to the negative 2nd power. I think it would probably be easier in this one to go ahead and distribute here. So this is a power of a quotient here. So I'm going to give the negative 2nd through multiplication to, actually the way we're going to do this one is let's go ahead and deal with this. And so what I'm going to do is I'm going to take the b to the negative 2nd and move it to the numerator as a positive exponent. So this will actually be b to the 5th times b to the 2nd. Now all that's still to the negative 2nd power. I think that'd be the easiest way to do that one. And that's still the negative 2nd power. So if I want to, I can just make that b to the negative 14th, and then I'll just make that 1 over b to the positive 14th. Make that a little better. So that's our final answer there. Alright, let's see if there's anything else on this page. I think I've got everything. is okay, so last page, you got a couple of real tricky ones up here. So let's look at this one. I've got all of this taken to the third power. So I think the thing to do is do some simplifying within the parentheses first here. So I've got -3. I'm going to put the r to the fourth and r to the -3rd together. I'm going to be able to add the exponents there. So that'll just be r to the first power. In the denominator, I'm going to put those together, -3rd times r to the 7th, r to the -3rd times r to the 7th, add the exponents there, and I'll get r to the 4th. I still don't have to do anything because I can do one more bit of canceling. I can cancel this r in the numerator here, and that'll make that r to the 3rd power. So I'm left with -3 over r cubed, all that cubed. So I can then make this -3 cubed over r cubed cubed, and so that would leave me with -27 over r to the 9th. Then I have here you have in this next example both of the expressions that are in their own set of parentheses to the -3rd power, so I better deal with them separately first. So therefore I'm going to go ahead and distribute in this one and make this 17 to the -3rd power, because I have power of a power product, and because that was 17 to the first power, and then I'll have x to the -15, I'm going to have to multiply here, y to the +15, and z to the -3rd. That's the numerator. In the denominator, I'm going to have 17 to the -4th, and x to the 20th. I'll have y to the -12th, and z to the -8th. You can kind of treat these separately. So 17 to the -3rd over 17 to the -4th times x to the -15th. This will just enable me to see things a little clearer. And y to the 15th over y to the -12th, and z to the -3rd over z to the -8th. So what's going to happen in this part right here is I'm going to, if I subtract the exponents, because I have the base is the same, -3 minus -4, that's going to mean add 4 to -3, so that'll just all be 17. And then I'll have, so I'm going to want to bring down in this one, so I'm going to want to bring down in this one I'm going to want to bring down the x to the -15th down here, so it'll combine, so it'll be x to the -15 will go to the denominators and x to the 15th, and that'll combine with this x to the 20th to be, so that's all going to be 1 over x to the 35th power. And then I'm going to want to move this -12 up to the numerator as a positive exponent, combine with that y to the 15th, so that's going to be y to the 27th power, and that's in the numerator. And then here I'm going to want to bring this -8 to the numerator as a +8 and combine with that -3 to make, so they would add the exponents there, and that would be z to the 5th power. And so all that together makes 17 y to the 27th z to the 5th over x to the 35th power. That's how all that cleans up or simplifies. Now the present value problem is related to the compound interest formula. The compound interest formula is actually amount equals the principal, so the amount in a bank account where you're investing P, the principal, times 1 plus the interest rate times the number of years you're going to be compounding interest. That's what the CI means, compound interest. But when you want to reverse that and you want to find what the principal would be if you wanted to end up with that amount, you would end up having the exponent being negative, and that's just a modification of this formula, fairly simple modification of that formula. So here's how this works in practice here. Okay, so let's move this up a little bit. So in this information, given this information, how much money must be invested at 9% to have $100,000 in 40 years? So what they're giving you is they're giving you what A is, that's $100,000. And so we can clean that up. And they're giving you R is 0.09, and they're giving you N to the, or negative N equals 40 years. So we'll substitute and we'll end up using our calculators here. So P equals 100,000 times 1 plus, we have to put that in decimal form, 0.09, and so that's going to be to the negative nth, so that's going to be 40. So remember, n is negative, so we're going to say negative 40 there. So then we'll plug that into our calculators just as is, and that will get us that we would have needed to invest $3,183 and 76 cents and earning 9% compound interest over 40 years to end up wanting to have $100,000 at that point. So this is the end of the lesson. You can start the homework.